Mars today is a barren, dusty world etched with the faint outlines of ancient river channels and vacated lake beds, yet once, its landscape teemed with flowing water. While remnants of that primordial water remain trapped beneath the planet's surface, researchers have long pondered the whereabouts of the rest. Recent investigations led by NASA scientists using both the Hubble Space Telescope and the MAVEN probe are now painting a detailed portrait of where Mars' water ultimately went. At the heart of this inquiry lies the process of photodissociation, in which sunlight cleaves water molecules in the upper atmosphere into hydrogen and oxygen atoms. The lightweight hydrogen atoms readily achieve sufficient velocity to break free from Mars' tenuous gravity, drifting into interplanetary space. In contrast, their heavier sibling, deuterium, a hydrogen isotope containing an extra neutron, escapes far more sluggishly. Over eons, this imbalance has progressively enriched Mars' atmosphere in deuterium, offering scientists a quantitative measure of water loss. To capture a comprehensive picture of this escape, Boston University's John Clark and his colleagues have synchronized Hubble's long-term ultraviolet observations, dating back to 1991, with MAVEN's in situ measurement since its 2014 arrival. By monitoring the flux of both hydrogen isotopes at various points in the Martian year, the team has stitched together a full seasonal cycle of escape rates over 3 Martian years, each equivalent to 687 Earth days. This dual-mission approach fills in gaps that MAVEN alone could not, particularly during Martian winter when deuterium emissions grow too feeble for its instruments to detect. These observations have revealed that Mars' upper atmosphere undergoes pronounced heating and cooling within mere hours, driven in part by its markedly elliptical orbit. Near perihelion. When Mars lies closest to the Sun, water vapor ascends rapidly to altitudes where photodissociation is most effective, spurring spikes in hydrogen loss. Additionally, the influence of solar wind protons and photochemical reactions injects extra energy into the exosphere, further boosting the rate at which both hydrogen and deuterium overcome Mars' gravitational pull. Beyond solving the mystery of the missing water, these findings carry profound implications for planetary science as a whole. Mars, Earth, and Venus occupy roughly the same habitable zone in our solar system, yet each has followed a vastly different evolutionary path. Understanding the mechanisms that stripped Mars of its once abundant water offers a crucial analog for assessing the history and habitability of terrestrial exoplanets orbiting distant stars. Published in Science Advances, the study underscores the value of combining orbital telescopes with dedicated atmospheric missions to reconstruct a planet's climatic past. As MAVEN continues to deliver fresh data and Hubble remains poised to capture ultraviolet signatures, the emerging narrative of Mars' transformation from a warm, watery world to the frigid desert we know today grows ever more complete. This research not only unravels the story of Mars' lost oceans but also equips us with the insights necessary to interpret the atmospheric histories of planets beyond our own.